Hi everyone, and welcome to the third in a lecture series on social research methods. This lecture will cover survey research. It's a major topic in sociology or political science and really in many different areas that I don't have time to list here. Here's the plan for today's lecture. We're going to talk about the purpose of surveys in the first place. Surveys in some ways might seem very natural, and people that have a lot of exposure to social scientific thought probably see them as sort of obvious tools, but in some ways they're not, and they have certain drawbacks that are worth mentioning. Then we'll go over some of the sort of basic terms, the jargon that you need to know in order to understand this lecture. A lot of that jargon can be daunting at first, but all the terms are used for some purpose, even if they're not necessarily immediately accessible to a novice, so I'll give you a sense of where some of those terms come from, why we use them. Then we'll talk about a general way of thinking about problems with basically surveys. So bias and variance are kind of the two primary mathematical ways that we think about the problems with surveys. And then we'll go over the sources of those problems, which don't map neatly onto the two outcomes, bias and variance, but each of the sources can cause each of the problems. So those are representation and measurement. It'll be kind of a dense lecture, and it'll have a coherent theme throughout, but I'll mention a lot of things incidentally that we won't be able to discuss comprehensively here. They'll have to wait for future lectures, but my goal here is to just provide you with an introduction. So here's a summary of the lecture just in one slide. Surveys are good tools for asking questions about relatively objective characteristics of a large number of people. What's meant by objective will vary depending on your interpretation, but generally speaking, what I mean is characteristics that all of us would agree, or most of us would agree, a certain person possesses or not. So things like someone's age or their income, as opposed to things like someone's state of mind at a particular point, which is known only to them, and oftentimes we don't know our own states of mind especially well. But any sample statistic that we gather using a survey is bound to differ from population parameters for obvious reasons. At a minimum, random error. There are some less obvious reasons as well. I'll say more about what's meant by these terms in a moment, but sample statistic, just for the moment, means something that you calculate with a given sample that you have at hand, such as the results of a survey, and a population parameter is something that you want to know about the entire group of interest. So, for example, you might be interested in the average age of the US resident population. The true value, which is unobserved, even if you take a census, for instance, we only take the census every 10 years in the United States, so it's bound to be outdated at a particular point that you ask. That would be the only way to really know that value for the population. So typically speaking, we don't know population parameters in statistics. So a sample statistic would be, say, if you had a random sample of about 1,000 people and calculated the average age in that sample, that would be a sample statistic. So for kind of obvious reasons, just because you have a small sample of 1,000 people, you might suspect, and this is a good intuition, that estimator is a good effort at guessing the true population average age. It is. But at the same time, it's going to, I think, just hopefully for intuitive reasons, not necessarily be the exact same as the true US population age. A way to think about errors in any sampling process, and this incorporates more than just random error here, is the notion of the mean squared error. That's what this notation here means. We read this as the expectation of the sample mean minus the true population mean squared. And an expectation, which I'll explain more in the lecture, just means an average, effectively. But we'll need to write and think in a way that's consistent with the very rich literature in statistics and survey research. So I'm not going to use some of those kind of other pieces of terminology that also sometimes do mean different things. The expectation, for instance, is a kind of a dense concept when you really get into it. But for our purposes, you can think about it as just an average. Y bar, which I'll explain later in the lecture, is just a piece of notation that we use for the sample mean. And this notation here, this is mu, the Greek letter mu. And mu, even though it kind of looks to some people like a U, it's actually a really curvy M if you think about it. You want to trace that M shape right here. And this stands for the population mean. In general, Greek letters like this will mean population parameters, so things that are true of the population. And then finally, this is squared. I'll say more about that later. So it turns out that you can decompose that mean squared error into two sources, and these really should be called like squared sources because these terms will be squared when you look at them mathematically, but we'll come back to that. Those two sources are the bias and the variance. And the bias is basically the difference between the average value of a sample estimate and the true value of the parameter squared. So if you imagine not this y bar in here, but actually the average of all the y bars, and then you think about taking the average difference between the average of the y bars or the sample means, and the true population mean, well, all that averaging doesn't really do anything in the end. Like this outside average doesn't do anything. And you just have fundamentally the difference between the average of all the sample means and the true population mean. That's the bias. And then the variation of the sample statistic around its mean, which is the variance. And that doesn't mean the variation of the sample statistic around the true mean. It just means around whatever mean that the sample process happens to have. And all of this refers, by the way, to this kind of notion of a sampling process, which can be a little bit tricky at first. So I'll come back to that and discuss that a little bit more later. And finally, bias and variance come from problems in representation and measurement, which I'll say more about later on. Broadly speaking, representation means how close is your sample to the population in the sense of being characteristic of it. And measurement refers to how good or precise are the questions that you ask of your sample. So let's start with surveys. Why do we do surveys? Well, our task as social scientists is to learn about human behavior, and we sort of have a raft of options. The first might be the most obvious. We could do interviews in ethnography, and an interview is different from a survey, largely in that you gather the data for an interview firsthand, and you typically let people speak to a large degree in their own words. Ethnography basically means the process of sort of just observing people, but observing them again firsthand, not necessarily even asking them a structured set of questions, but just kind of, oftentimes participating in the activity that they're participating in, but keeping notes. Or sometimes you might be sort of a semi-participant, etc. We'll come back to that at the end of the course. The upside of this is that we get to use people's own words for the most part, and we get, as a result, this rich, holistic data. The downside, and this is really just the function of the richness of the data, is that it's hard to generalize. So by definition, to compare across these different locations means that we have to compress and compare the information that we have. So we're kind of left with this problem that we can write like a really novelistic and deep ethnography, for instance, but it's going to be hard to compare that to other ethnographies unless we're willing to make some oversimplifications, for instance, right? And by oversimplification, I just mean simplifying it all, saying, well, your scenario was like my scenario in this, that, and the other way. The problem is that at that point, you're sort of already giving up some of the detail that's intrinsic to a good ethnography, and that's just a trade-off you generally have to make between universality and particularity. Another option would be an experiment. The upside of these is that they allow us to examine balanced groups, which can let us infer causality. This is kind of going to the opposite extreme of an ethnography, where we have a setup where instead of just observing things more or less as they are, we're saying, let's actually set up the world just the way that we would want and see what happens. The downside is that this is often unrealistic, and causality is not the only interesting question. Sometimes we might just care about associations between two things, so not worrying about whether or not your your education actually causes a higher income, but just whether or not these are associated. And then finally, we've got the option of surveys. So surveys, the upside is that it's easier to work out how the sample generalizes when we just want simple summaries. So unlike interviews in ethnography, generally speaking, there's a pretty rich literature on surveys and how they generalize. People do write about how to generalize interviews in ethnography, but there's, I would say, far less agreement on that. It's not really got a mathematical scientific component behind it. And then compared to experiments, if we don't really care that much about causality and we're willing to tolerate some fuzziness in that way, just so that we don't have to go through all the effort of an experiment, which in most social science cases really isn't very realistic, surveys are the way to go. The downside is that we have this extreme data compression. So when you ask people to characterize, say, their feelings towards the president on a Likert scale, which is one of those, kind of heat map things where you say, I strongly agree, feel neutral, disagree, strongly disagree, that sort of thing. That obviously to a lot of people strikes them as kind of, somewhat artificial, and indeed it is, but that's a downside of surveys. So all of these options have different upsides, different downsides, and today we're going to talk about the challenges in surveys. So what are surveys good for then? Why would we use these? I said a little bit more about this in the last set of slides, but I just want to kind of stress what we're up to when we use these things. When we're interested in relatively objective variables such as income, education, home ownership, number of children, the act of gaining or losing a job, occupation, professed religion, or binary outcomes or opinions like supporting or opposing a policy. So where you don't have to, ask someone to characterize a deep psychological feeling, but maybe you just care about their, opinion on a contested matter. It's also useful when we care about simple group level properties of those variables, such as the true population mean or the variance, which I'll explain more in the lecture, but basically means the spread, or the relation between one outcome and one or more predictors. So something like the relationship between education and income, or the number of children you have and your professed religion, something like that. That's when surveys are relatively useful. It's also useful when we care about a large group of people to whom we do not have access, or direct access anyway. So something like the U.S. resident population is a common population. By the way, when I say population in the general sense, I mean that this is just the total group of people whom we care about. I'll say, again, more about definitions later. So population doesn't always have to mean literally the entire group of residents of a country, which is usually what it means outside of a technical context. So what aren't surveys good for, which is something that we should also think about? So they have a relative disadvantage when we're interested in subjective states of mind or feelings. As I mentioned before, researchers do often try to ask for such information in surveys, but I would take these results with a strong grain of salt. Those Likert items, many people feel are inadequate ways to characterize their feelings about things. If we care deeply about causality and not just association, surveys are also not that great. Some kinds of quantitative data do work well for this, although this is where qualitative data really shine. But when we use quantitative data for this, we usually need panel data, which are repeat observations of individuals over time, and that's such a special kind of surveying that we can't treat it here. Finally, if we care about a small particular group of people whom we don't think are really that representative of other groups, so for instance, you might have an interest in, say, the Amish community, or you might have an interest, say, in the specific ways that, let's say, some subset of a sports fandom in Chicago specifically makes meaning out of Bears games, something like that. That would be a scenario where there's really very little use to having a survey unless you simply have trouble locating enough people. But if you're really interested in a particular limit case, as we call it in sociology, so, in sociology, we generally shouldn't study specific groups of people and say nothing about the broader world, because part of what makes sociology something of a loose science is that researchers talk to one another and build off their findings. So that means that you can't just study something purely because you have an individual interest in it, but sometimes we study things that we think are interesting largely because they're very unique and they're kind of hard to generalize. The general conclusions are oftentimes not, something like this group is representative of the broad population, but actually the opposite. This group is very unique, and that tells us something indirectly about the broader group. If you're doing that kind of a project, then generally qualitative data are the way to go. And again, like qualitative data, I'm just going to mean, roughly speaking, that you gather data firsthand. You don't constrain the responses to a particular format or style of response, like please write down a number, or please pick a Likert item, or please choose your race from this list, that sort of a thing. When you do have that type of response, you have quantitative data. That's just the way I define it. Other people have different definitions, but I think the way that I do it more closely reflects the actual differences between these things, rather than saying something like qualitative data don't ever involve numbers, because obviously they will some of the time. You'll have to count the people in your interview group. Your participants will mention things to you, such as about 50% of the time I go to church, something like that. and it's impossible to really say that it's just this difference in numbers or not. So let's introduce some of the survey jargon: whom we sample and why. So just to establish, I've already used this term a number of times, but so everyone's on the same page, a survey is a set of questions about important issues that we'll send to respondents who will hopefully answer them. In any study, but this is especially true of survey research, we need to begin with a clear idea of whom we want to know about, the total group of people to whom our conclusions apply, and that is the population. So again, population just means the group of people that the survey is functionally about, not just the group of people in the survey, but the group of people that we think this sample or survey is a random, or sometimes not random, but is a subset of. The group of people that we have actually access to is the sample. The sample, again, is formally speaking a subset of the population, so all the people in the sample should be members of the population, although sometimes we'll sample from maybe two separate groups, but we think one group is an adequate representation of a second group. So an example of that might be that if you, for instance, happen to not have anyone from the US state of Rhode Island in a sample, that could be problematic in a lot of cases, but in some cases you might be willing to say Rhode Island is the smallest state in the union by population, or maybe it's Wyoming actually, I can't actually remember. Rhode Island is the smallest geographical state, it's one of the smallest population states. Probably Wyoming is the smallest population state. But anyways, maybe you leave out people from Wyoming, let's say, and you may not really care for certain purposes whether or not that's true, although in other situations you might care quite a bit. It depends. It depends a lot on a lot of different factors. Anyways, that's a side issue. In general, the sample should be a subset of the population, though that would be ideal. And we denote it using this terminology here, which you'll sometimes see that the sample is a member of, that's what this notation means, is a member of the population. And this is like kind of a wacky looking version of a Greek E or an epsilon, which has to do with the word for is in Greek, just so you know. So the population can be finite, and that's typically the case when we deal with basic survey methods. So for instance, the total US resident population at a particular point is finite. And by the way, populations, anytime we try to do inference about a really specific fixed population, we're going to run into some trouble because, as you can tell, you could look this up on the internet, how often is someone born or how often does someone die in the United States? By the time I finish this lecture, there will be a lot of people who have been born and a lot of people who have died, relatively speaking. Or maybe not relatively, actually more like absolutely. In relative terms, it's quite insignificant, but in absolute terms, it's not the same population. So we kind of have to then think about the problem of sometimes our populations are a little bit hard to define exactly. So that doesn't mean that they are infinite, which is why I used this other word, non-finite. Infinite population might imply that it stretches on forever, but non-finite might simply mean that it's not unbounded numerically, but it's always kind of shifting. There's people entering or exiting at the margins, and if we do this survey, like let's say, it takes us 6 months to publish a paper that's, based on research results done today, something like that, or survey results done today. What we might say is, well, the population has changed a certain amount, but we think it's kind of functionally the same thing. And actually, this is kind of a nice way to think about the problem, because in classical probability, a lot of times the population in the simplest probability examples, such as flipping a two-sided coin or a six-sided die, the notion of the population is actually a little bit tricky, because what is the total population here? If we take a sample of 10 flips of a coin, what are we doing inference on? And really we just mean the long-run behavior of the coin, but there isn't a finite population of all possible coin flips, right? So sometimes that perspective, that actually classical probability examples oftentimes don't have a finite population, is helpful, because sometimes we'll need to say, well, the population is actually a little bit hard to define in terms of a fixed set of people that won't change. Instead, it's sort of a concept. It's like the typical character of the people that live in the United States at around this point in history, something like that. That turns out to really not matter very much at all, but it's something that when you really stop and think about the words I'm saying might cause some confusion. At some point, most people kind of stumble upon this, so I just wanted to mention it. Okay, so now that we've talked about the basics of surveys, we need to talk a little bit about what can go wrong with them and what we might do to solve those problems. So we're going to start with the notion of the total survey error. And the total survey error, here I just said survey error, but when I say that I mean the entire survey error, refers to the difference between a population parameter, such as the population mean, and a sample estimate. We're going to use means throughout this lecture because they're the simplest type of statistic or parameter to deal with. We'll denote means with the Greek letter mu, as mentioned before, or if we need to clarify, we'll write mu y, where y is just the variable in question. Sample estimates, again, will often be denoted y bar. Sometimes you'll see, and you'll see this a lot later in the course, sample estimates denoted not with a bar, but with a caret or a hat over the parameter. So you might see mu hat, which would be mu with a little caret here. That is more consistent notation, but this older notation is more common, so I'm going to use it here at first. Also, partly as a reflection of that, you can't easily write carets on things in Google Slides. We'll actually use a document written in what's called Markdown, which is a way of writing that incorporates LaTeX, which is the kind of premier, by far, way to write math on a computer. So that's partly a reflection of this older terminology. So later we'll see mu hat used to denote things like a sample estimate, so the sample mean, which is just the mean in the sample. But now we'll denote it y bar. So the tricky thing about statistics is that for any given sample, it's actually pretty hard to say how much error there is, and that's really what makes it statistics. So if we knew exactly how wrong any given estimate were, we wouldn't be doing any actual inference, right? There would be no inference left. So if I gave you a sample and I said, okay, the mean in this sample for education is 13 years, but it should actually be 13.2 years because that's the population value, then you don't have any statistics left to do, right? You just know the answer. But if I gave you that answer, I would just be giving you the error. I would be telling you that there is a negative 0.2 error in your estimate. So for any given sample, we can't know how much error there is. But what we can do is say something about the process of, let's say, taking a sample mean from a simple random sample. And I mentioned this point above that I'll just use means throughout the lecture here, but there's other kinds of things, such as a correlation coefficient or a standard deviation or a regression slope. These are all slightly more challenging to deal with, although we'll see some of that later in the course, so I'm just going to start with the mean. So we don't know the error for any individual sample, but we can refer overall to the sort of error of the process. And in particular, what we're going to hope to do is reduce the bias and the variance of our process so that the mean squared error, MSE, which is written like this, again, what this tells us is this is the average of the squared difference between the sample means and the population mean, is as small as possible. I want to give a brief aside on variables and parameters because this can sometimes be confusing. So it's important to keep random variables and population parameters straight in your head. Here's a quick guide to the differences. Parameters are fixed properties of a population. So for instance, the mean income right now of the entire US population. They don't vary with the sample, so they're not random variables. We often represent them with Greek letters to keep them apart from random variables, which are typically things like X and Y, so those are Roman letters. And it doesn't really matter, upper and lowercase with Greek letters doesn't really matter, which is a good thing because most people, even if they know the Greek alphabet, like I do, I sometimes forget what's capital and what's lowercase. So if you see a Greek letter, it probably means a parameter, and there's nothing more to it. We typically don't have direct access to these, and doing inference on them is statistics. So we aren't going to know, for instance, the true mean income in the United States right at this moment. Short of having census information about this, and to be fair, I'll use a lot of examples where we do have census information from a few years ago about this sort of thing, but the point is to learn to do statistics about any old thing, including stuff that the census may not gather information on. So that's parameters. Variables vary with different samples, hence the name. They also vary across individuals, so there's kind of this interesting double meaning there. But something like, for instance, the true mean of the population, that doesn't vary across individuals because it's a group level property. But even a sample mean varies because it's not the same from sample to sample. So even though every individual in a given sample has, quote unquote, the same sample mean. It varies across different samples. So variables proper have that kind of quality. So for instance, the mean income in the general social survey varies across different samples or different waves of the GSS, or you could really say that even though on a particular GSS it's fixed because it's just a quantity in the data, it was something that could in principle have varied if the GSS had been gathered in, we'd had different kinds of random variation in the people that participated. These are often represented with Roman letters, and here there is an important difference, although you won't always see this done consistently, but typically speaking, capital Roman letters like capital Y or capital X mean a random variable. So for instance, to go back a slide or two here, when I write capital Y bar here, this means the concept of a sample mean. So this is the sample mean as a random variable. So again, we deal with sample means in terms of like actual sample means. So we take a sample, we get a mean. This refers instead to the abstract concept of one. When we see lowercase Roman letters, that typically refers to some realization, so some actual observed sample mean. So with this we do have direct access to, but the problem is that we aren't sure how it relates to the population. So we use this information to do inference. So we're doing inference using sample properties to learn things about population properties. So the total survey error can be decomposed in a couple of different ways. One way to think about it is bias versus variance. So what makes a sampling process good? It should have minimal bias and minimal variance. Bias is the effectively average of many estimates for a given sampling method not being equal to the population value. I'll explain the graphic in a moment, by the way. Variance is that the spread of many sample estimates is high. So let's look at an example with low bias and low variance. We have low bias in this particular scenario because we can see that imagine this target, like the center of the target is the true population value, or it's just, you don't even have to think about the metaphor that carefully. You can just see like these points are really close to what we would consider a target if this is a dartboard. So the points, if you think about like their center of gravity almost, which is actually basically a mean in 2 dimensions, it's really close to the center of the dartboard. So that means that there's low bias. The average of all of these points location is close to the location that is the true one, the target. It also has low variance, which means that the spread of these things, even though that's a little bit hard to quantify, like maybe this seems like a lot of spread to you, variance, generally speaking, is always relative. There's ways of basically comparing variances called the coefficient of variation, but we're not going to get into that. The variance here, it's subjective, but you can see that by a lot of people's standards, you would say these are pretty closely clustered. It's kind of hard to see much daylight between them. Maybe it's helpful to look at a counterexample. So in this case, we've got high variance and low bias. And it may not be obvious at first that there is a low bias here, but again, if you think about sort of the average position or the center of gravity of these points, it'd probably be something right around here maybe. And so it's not far off the target. It's probably in this red area, but you can see that the spread has gotten larger. Conversely, you could come down here and look at a case where your estimates all kind of cluster in the same area, but they're noticeably far away from the target. So this would be a situation where we have high bias and low variance. And the worst kind of sample would be one with high variance and a high bias. So that would be one like this, where you can see the center of gravity of these points is quite far away from the target, and there's a lot of difference between the individual samples. So again, I want you to just kind of pay attention here to this fact that'll become a little bit tricky later on. Fortunately, it's maybe not that tricky yet because we haven't learned even basic statistics, but you'll see that once you learn basic statistics, sometimes it's easy to mix up statistics about a given sample and statistics about many samples because they're quite different, even though we use some of the same tools. So here we're talking about this sort of meta process, the process of taking many samples. And you may know or may not know that you actually can't take many samples in most situations. You just have the one sample. But it's still important to think about what process did that come from so that I can know some things about the sample's properties. So let's go over this one more time, but with a mathematical derivation, but also a nice, more realistic example. So here's how we write bias and variance with math. When we say that we don't want any bias, we're hoping the expectation of y bar is equal to the true mean mu of y. So if the expectation of y bar, and expectation again just means the average for our purposes, is not equal to mu y, or in other words, mu y bar is not equal to mu y, our way of drawing means is biased. And what I want to call attention to here is this somewhat silly thing about notation, which is that expectation basically means average and mu basically means average. They both mean the mean, effectively. But this expectation operator here basically is like writing a formula. There's actually a formula for the expectation I'm not showing you. Basically, you take the probability of each observation times the value of the observation, and then you add them all up. But this is kind of like writing the formula out, and this is like writing the result. So this is, if you think about like your basic, intro stats, your stats that you learned in grade school, this mu here is kind of like writing the word average, and this right here is kind of like writing summation or total over n. So they're just slightly different ways of writing the same thing. We also hope that the variance of our estimator, the expectation of y bar minus mu y bar squared, is small. And by the way, you square this before you take the expectation, just so you know. Note that this is the variance of the all the sample means around the mean of all the samples, mu y bar, not necessarily mu y. So what this is doing here is this is isolating just the spread. So even if this mu y bar is not equal to mu y, which would mean that there's bias, it could still be the case that the spread of observed sample values around the mean of the all the sample values is, sorry, I should make that clear, all the values of the sample, and we square it, that could still be small. So the variance, or in other words, the spread of different sample means could be small. Together, and there's a proof in the back, these happen to sum to the mean squared error of the process, which is what we want to minimize. Here's an example of a couple of sampling processes. What I did here, I wrote a simulation using Python, is I took a very large survey sample and I treated it like a population. So it's actually a sample, but it's hard to find population data. So I took a large sample and then I took a bunch of small samples. So I basically sampled the sample. This is actually a process called bootstrapping, and it's pretty common. So it's not anything weird that I just made up. And basically what I did is I took a bunch of samples of two different sizes. I took one where n is equal to 20, and then I took one where n is equal to 100. And then I found the mean of mother's education. I didn't do this by hand, of course, but I made the computer do it for me. I took the mean of mother's education in each of those samples of each size. And then I plotted those on a histogram. So these are the values of all the samples, or the sample means. And then this, don't interpret too much here about the meaning of the y-axis. This is density, which we'll come back to. Basically, though, you can think about this as a histogram. So basically, where you see taller bars here, there were more observations in that area. And then when you see shorter bars, there were fewer observations, say with a value of like 10.5 or something. And then finally, I plotted the mean of the larger sample means here, and then the smaller sample means here in green and red. And then I plotted the true mean, the one that was just in the entire sample, or here I'm just going to call it population from now on, in black. So what do you notice here? Well, the means of all of these processes look to be the same. And you can kind of see that the center of each distribution is the same. But there's noticeably more spread with the red bars. And that's because we have a smaller sample size here, so there's a larger role for freak coincidence, basically. Because each sample has less information and there's less chance for, an absurd sort of person entering the sample to be balanced out. If you want to think about a really extreme case, if you just plot every person, like you take a bunch of samples, all of the size 1, the distribution may look really wacky. It'll actually really just depend on the distribution of the underlying variable. But when we have samples, those sample means are drawn from much nicer distributions. There's actually a very deep fact that's called the central limit theorem that we'll discuss later in the course. Now let's illustrate bias. So we just saw an example of variance, but let's look at bias. So here's a situation where I basically took samples of the same size, each of 100 people. And the number of replications in both of these cases, by the way, is 5,000. That doesn't actually matter because this is just illustrative. So in practice, you should care about your sample size, but you won't do replications. So the number of replications here, I just picked a large enough number that the patterns become apparent. So what's going on here? Well, in this case, I told Python to deliberately oversample people that mentioned that they had fundamentalist religious beliefs, and then I took the sample mean of their mother's education, and then I did that for 5,000 replications, and did the same thing here for just random samples from that population. And in each case, the sample size was the same, so we had samples of size 100. I'm not meaning to knock religious people here, by the way. I'm actually quite devout myself, but I don't talk about that beyond just mentioning it when it's relevant. But I just thought, there is a known fact, this is something that's true of my community and those of others, that there, generally speaking, is less education in that community, less formal education. So you can see here that the black bar is, again, you can barely see it. It's kind of over or under this green bar here. But the true population mean is like right around here. And you can see that the center of these green bars, these random samples from that population, which I also plotted in green here, those are basically the same. So that's a very unbiased process. You might also note that the spread of these red bars is almost the same as the spread of these green bars. So you can see, if you think about almost like the shoulders, so if you have a normalish curve like this, normal just means the bell curve shape, we'll say more about that later. If you have a normalish curve like this, you can almost think about the shoulders of this person. That's about, in most cases, about 1 standard deviation away. Standard deviation, by the way, is just the root of the variance. Again, if I mention some of this stuff quickly in passing, don't worry, we'll go over it later. So you look at the shoulders here to get a sense of the spread, and you can see that the shoulders seem to be about equally far apart in both cases for both distributions. But the mean here of this distribution is noticeably too low. So there's a bias in that individuals that reported that they were about, when I sampled people where, to get into the sample, there was a 90% chance that you'd be a fundamentalist, basically. What that means is that in this case, has a lower mean. And it's a lower mean by almost a full year of education, maybe actually closer to about a half year of education, but substantial, right, when you consider that it's an average. And you can see that these distributions, otherwise look quite similar. So this would be an example of a biased process, but one that's essentially got the same variance as another process. By the way, you can have processes that have zero bias, but it's almost impossible to have sampling processes that have zero variance. So finally, let's combine the two just for good effect. And I'm actually redoing the whole simulation here, so I'm not just combining the last two slides. Ignore this talk here for a moment and just look at the picture. You can see in this case, what I went ahead and did was I got a smaller subset of people. So this is just 20 people per each sample. And then I did the same thing where I picked a sample that had a 90% chance of including individuals who reported that they were fundamentalists. And then I did just a simple random sample of size 100 of the same population. You can see that the mean of that process is the same as the true population mean for the green bars, and the spread is significantly less. So this here in red would be a high bias, high variance process because it's got a lower mean, and the spread is visibly larger relative to this low bias, almost no bias, and low variance process here. So that's an illustration of what these things mean. Hey folks, I'm going to dive in just right here. This will probably be kind of an awkward jump cut, but I realized that I didn't bother to explain some of these terms in this diagram, which you haven't seen before. So even though a lot of the terms are somewhat familiar and I explained some of them in the video, I do want to just go over briefly what each of them means. So remember that the population, and you can just ignore the difference here, so just consider this the population, is the true group of people that we care about and are interested in knowing about. Sampling frame, I do explain in this video, it's basically the list of all people that we'll even try to contact. The sample is the people that we actually do contact, and then there's a difference sometimes between the people that respond at all or end up in the sample, and then the people that actually end up responding. So the sample is the people that we actually contact, and the respondents are people that actually respond to the survey. Coming over here to the measurement side of things, the construct is the concept in all of its conceptuality in its full abstract form that we're interested in. Measurement is the actual questions that we ask of people, response is the actual answer that they give, and then the edited data are the actual data that we get. So you might wonder like how these things could differ. A construct, for instance, might be someone's income. Now that sounds very easy to measure, but it turns out income comes from many different places, and sometimes you might forget to include a possible source, and a respondent might forget to mention it. So that would be a problem of measurement. The actual questions that you ask people about their income are how you measure it. Then their response could be different from what the actual value of their income is. So they might under or over report it, for instance, and that would be the response being different from the measurement. Then finally, in the process of transcribing, people might somehow corrupt the data in different ways, and that would be an example of processing error that gets you, to the edited data. So with that, I'm going to let the lecture resume, but I thought it could be useful just to get a quick pitch about what all these things are, even though I explain some of it a little bit later. So now let's talk about the sources of bias and variance, and we won't focus too much here on the mathematical details, but I just want to inform you of the the other ways that we can kind of chop up the total survey error. So the total survey error can be thought of in terms of the results. You've got bias and variance, but you can also think about it in terms of the sources. And we'll focus here on this diagram, which is basically just a more detailed version of what you saw in your reading. So bias and variance have these two fundamental sources. The first is the problem of measurement, or the adequacy of the actual responses to our actual set of questions, capturing, that should be capturing, not captures, some theoretical construct. So that's combining a lot of stuff here. I'll say more about that later. But to put it in simpler terms, it basically means how well do the questions that we actually get people to answer, so the actual questions that we write that are actually answered, how well do those things match the thing that we are interested in? That actually doesn't have anything to do with how good the sample is or who answers the sample. It sort of does, but you could say it really is like more about how well actual responses to actual questions, regardless of whom exactly we are asking, capture some coherent idea that we care about. And the second is the problem of representation, which on the other hand is how closely our sample gives a picture of the population. So you can think about this as like, this stuff is primarily, although not entirely, about how well we write our questions, how much room for interpretation or confusion there is with them, how well we just manage the data. And then this stuff is like, how good of a guess at the population is our sample? So we'll go through all of these in a little bit of detail. So let's define these two problems here in the representation process. We're going to just focus on that side first. So the question here is simply, what traps do I avoid to get a representative sample? And we want to avoid coverage error, non-response error, and then minimize sampling error. So coverage error is when we systematically fail to contact certain individuals, and non-response error is that some individuals who end up in the sample systematically don't respond to the whole survey, or they don't respond to specific components of it. So let's give some examples. A classic example of coverage problems is that sampling frames, which is a piece of jargon you should know. It's the list of all members of the population whom will even have a chance of sampling. So coverage problems are when those sampling frames miss people. And I'm really loath to use stock images in my slides, but I did use a stock image here because a lot of you may not even remember what this is or may not know. It's a phone book. So sampling frames used to rely often on phone books. They're cheap, publicly available, and relatively comprehensive. So literally people would just get a list of all the individuals that live in a particular area and then dial those people up. This is kind of problematic though, because it can miss people. So it can miss extremely poor or rich people. And depending on the question you ask, that might bias things or it may not bias things that much. It depends on whether or not, say, if we're thinking about income, maybe those poor and rich people balance each other out. But maybe for certain other things like, the sake of, let's say, asking people, let's suppose maybe that the extremely poor and the extremely wealthy are both unlikely to appear at sports games. So maybe the extremely poor can't afford it and the extremely wealthy are paranoid like Howard Hughes and stay in their houses all day. If that's the case, then obviously our sample will be biased towards, that'd be a better way to say it, biased towards people that tend to attend sports games. Okay. Now let's look at non-response. This is something of a complicated graphic, so I'm going to explain it to you really quickly. What this shows here is for men and women both, The authors of this study got access to a survey where they had to get some really special permission to then ask people, not ask people, but actually just look up those people's true income according to the government, basically using tax records. And then they compared that to basically, well, not even compared, I should say. They basically then figured out who didn't respond to a survey about income, and then they looked at the relationship between the person's income and whether or not they responded to the optional survey. So what this shows you here is that depending on someone's percentile DER, you can just ignore what that means. Basically, this is the income percentile. So the y-axis is the percent of non-response. And you can see that for a variety of different questions here. So this is earnings full-time, full year. This is average hourly earnings. So there's slightly different ways of asking this question on the current population survey. But basically on that survey, the people who didn't respond, so the people that had these really high percentages of non-response, were the poor and the wealthy. That's a really interesting fact that I mentioned just a moment ago. So this would be a case of item non-response. So in this particular case, you have wealthy and poor people who actually end up in the survey, so they were not omitted from the sampling frame. That's the difference, by the way, between this coverage problem and non-response. The point I was just mentioning with the phone book is maybe you don't even survey these people at all. You don't even try to ask them a question. But what we're seeing here is that when you do actually ask people questions, sometimes they don't respond, period, or they may not respond to certain items. Here, they're not responding to certain items, but they otherwise filled out the survey. And the non-response is generally higher for smallest and largest deciles. You might wonder why. I would augur that, that's not the right use of that word, sorry. I would probably guess, let's use a less pretentious word, that has something to do with, again, this general, desire for privacy among people that have kind of unusually high or low incomes. That would be my best guess. So does this cause bias? Again, maybe not. If the non-responses balance each other out, maybe it doesn't cause any bias, but it certainly could. It would really just depend on the exact way the numbers work out. Probably it does cause at least a small amount of bias, and it could potentially be severe. You might be interested to know that this actually happens to lessen variance, believe it or not. So this actually could, in a certain sense, be a good thing. So if this doesn't cause much bias, but it does lessen the variance, that's actually kind of a nice fact about it, even though it seems like a problem. The reason for that is that when you have high variance, or sorry, I should make that a little more clear. When you have higher variance in the actual sample itself, so not the variance between different sample means, but the variance of the underlying variable in the sample. I know this is a little bit tricky to talk about without the mathematical background, which we'll get to later, but just imagine spread in the sample on income versus spread across sample means of income. Those are the two differences I'm making. When you have less spread in the sample mean of income, it turns out that if you always observe less spread in the sample mean of income, you're basically going to end up with a process that is itself got less spread to it, or less variance. And if it doesn't cause a large amount of bias, it's actually a good thing. And again, the basic logic is that if you don't have these extreme cases, you'll have fewer sample means that have extreme values just by coincidence. It might be useful to think about a really extreme case of having no variance in a sample. So let's say that you are friends with some kind of wizard, and this wizard really likes your work and wants you to succeed. And so the wizard, whenever you get a survey, erases everyone's actual answers and instead puts in the true population value for the mean income. These sample means that you get from this process would obviously be unbiased. They'd be exactly correct, and there would be zero variance. But this would actually be a fine procedure if your only purpose were to estimate the population mean. Now, you might want to do other things like look at the spread in the sample as a way of estimating the overall distribution of income, and then the wizard would have done you quite dirty, because that would be very useless data for that purpose. You just see a bunch of people with the same exact income. But that said, just for the purpose of estimating the mean income, having this compression of a sample doesn't actually mean something bad. And that's a point that Salgonic makes in the article I assigned, or the book chapter, I mean. Okay, so let's finally talk about sampling error. You might have noticed that I skipped this term in the middle, sampling error. Sampling error is worth dealing with on its own because it can't be fixed even in theory. I just mentioned that extreme case where you had this magical scenario where you didn't have any sampling error, but in general that is impossible in reality. So this is the essentially probabilistic dimension of statistics. Basically, sampling error just refers to cases where when you go from the sampling frame or the list of all people to an actual sample, there's going to be differences between those two things. So you are going to get a random subset of the sampling frame if you do randomly sample, and that means that there will just be differences every time you take a different sample. So imagine a simple example where UW-Madison admins want to learn the mean income of students. They have a complete list of the target population, so they don't have coverage errors, and they could easily require responses by, say, not allowing you to enroll until you respond. And in fact, they kind of basically do that already. So there's no non-response error, or these things would be very minimal. But there would still be sampling error because if they just pick a sample, the sample means will vary from sample to sample, and this has to be dealt with. And you might even wonder why they would sample then in that case if they have complete coverage and little non-response. And the reason, this is something that Solganic mentions that's oftentimes undercovered, not to make a terrible pun, is that doing censuses or cases where you actually ask everyone in the population the question is time consuming, and then as a function of time it is costly. And there's also very little information added after a certain point. So even if you're not fully on board with this stuff and you're like, wait, how do we learn stuff from a random sample? That sounds crazy. Maybe you could think about it like this. What if you surveyed 80% of the US, or the UW-Madison student population got their mean income? And let's say that first 80% is truly random. So it's just a random subset, very large subset of the UW-Madison student population. How much do you think you're really going to learn from that last 20%? Is it going to be a lot or a little? And hopefully it's intuitive to you that the answer is actually probably not very much. And then the less intuitive step that I'll encourage you to take later on is simply that you don't even need to sample anything close to 80% to basically come to the same conclusion, that you're not going to learn a whole lot more from getting more and more people. So that's sampling error. Sampling error also fortunately does not cause bias in and of itself. In the case of the mean, there's actually only two ways to reduce it. You can reduce the variance of the variable itself in the population, or the variance in the sample you observe, both of which are bad ideas. Remember my example with the wizard. Or you can increase the sample size. So again, even as I mentioned before, the former is generally a bad idea because even if you don't have any bias, like reducing variance in the sample doesn't induce bias, it would render the data less useful for other tasks. So again, even if you have a sample that happens to have everyone just lies and gives you the population mean as their income, then your sample mean is going to be a great estimator of the population mean, but you can't do things like look at the correlation between education and income because there's no variance at all in the income, and that means you can't take a correlation. So the latter, increasing the sample size, is a good idea for many, hopefully quite intuitive reasons. So that's a little more on sampling error. So sampling theory really needs its own lecture, and I'll deliver that on Wednesday. For now, what you can know is that we just like random samples, whether they are simple, that is to say fully random, or stratified, which means that they're random within groups whose size is fixed, since that random component makes the shape of the new the sample means predictable. So remember that bell curve kind of shape that you saw in those histograms of all the sample means. I didn't call attention to it, but I mentioned it briefly that that's actually quite an important point. It's called the central limit theorem, that they have that shape. And that is only true when the samples are random. When they are not, we get unpredictable shapes to those, what are called sampling distributions. So you should avoid samples that have no random component at all. It's okay if they're not fully random. Most samples aren't fully random, but you need some randomness in the process. Okay, so now let's turn to measurement problems. And let's start with something simple. Processing error occurs when survey workers make transcription mistakes. This is a little more of a personnel problem than a statistical one, and with computer interviewing, it arguably becomes less problematic. In short of fraud, you would hope that these aren't biased in any one way. By the way, if you want to read an interesting expose of a recent case of fraud, click on the link. But I should note that these errors do add variance even if they have mean zero. And that might be a little bit surprising in itself, but if you think about it like this, if the transcription errors are basically just random, so if someone adds a column here or there, or mistakenly writes down the wrong number, or they can't read their own notes and they take their best guess, and the guess is unbiased up or down. That's not going to add anything to the mean of the responses, but basically because you're adding this random variable, it turns out that when you add together two random variables and they're independent, and in this case, it's simplest to assume that processing error would be independent of the responses, like it doesn't have anything to do with the value of the responses. Then you can just add up the variances and they sum together nicely. Although in this case, the problem is that means you're adding more variance to the actual random variable, which is not the random variable in itself, the income of people, but instead it's the income of people plus some true noise component. Measurement error, conversely, refers to deviations of a given response from the underlying true response. And this is kind of the ideal scenario. So imagine that there's no processing error. In the ideal, what's sometimes called true score model, you would still probably see some amount of measurement error, but the measurement error would just kind of be random small deviations when you record someone's responses. This can seem a little bit weird in a social science context, but what maybe is a little bit easier to make sense of would be in the case of a natural science context. So consider someone having their blood pressure taken. We'd expect some day-to-day fluctuations in the machine, so the machine doesn't measure it correctly, or there's some kind of flaw in how the nurse applies the cuff or something like that. You could think about it as not quite a processing error because it doesn't happen in the writing down of the responses or the management of the responses, but instead it happens when you just take the error. So in a situation like that, that's a good example of the kind of true score model at work. You'd expect some day-to-day fluctuation, or even just reading to reading fluctuation. And in fact, if you look at medical data, that is what you see. But it's not going to have a particular direction, and it'll be contextually small. So it won't be huge. It might be like a % deviation or something like that. And this is kind of the ideal situation. That would be another scenario where there's no bias, but we add some variance. However, it can get more complicated. So the errors could have a non-zero mean. This would be relatively simple. So say a given scale adds 5 pounds, you would just subtract it. Or the errors have a known variance that's higher than we'd like. So maybe if you have like a gold standard type of measurement, say a blood pressure machine that is just everyone's like, this is the ideal way to do it, but maybe it's really expensive and not every hospital can afford one, then what you could do is compare the variance of your actual instrument to the one that is the gold standard, and then you could adjust. Those would be good scenarios. Bigger problems would include a situation where we've got an unknown and large mean. So for instance, if you're asking people survey questions and you suspect that they, I'll give an example of this in a moment, suspect that they systematically underreport the true value, but you don't know by how much, that's a problem. And if you have errors that are correlated with the variable or other variables, or the errors of other variables, those can all be problematic. So what would that look like? Well, for instance, you might have, say, well, let's get to the examples. So the example I gave before, the large mean, for instance, if you ask everyone how many laws they've broken, you'll probably get an underreport, but you may not be able to say how much, right? The errors might be correlated with the variable or other variables. So for instance, the error term on a variable where you ask people about their drug use could be mean 0 for light users, but mean negative for heavy users. So heavy users might tend to underreport. And in this case, the error is not actually random. It's not independent of the measurement, but it's correlated with it. And in this example up here as well, you would say the problem is that we not only know that the mean is not actually, the mean is not just large, but it's also unknown. We can't actually subtract off the right amount. Okay, let's finally come to validity. So if the random noise associated with an estimator is relatively large, we might even go so far as to say that it lacks validity. So responses to our question are not really measures of the concept at all. It's kind of hard to totally pull apart validity and measurement error. So when there's a strong signal relative to the noise, we can call this measurement error. But when there's a very weak signal, we might begin to call this validity error. Here's an example. If I record someone's hourly wage and then tell them to pick uniformly distributed rational numbers between -1 and 1 out of a hat, that's very artificial, but just to try to pick a scenario that's super close to the theory, this would be classic measurement error. So their wage really isn't going to be that different from what it truly is. But if I make them pick numbers between -100 and 100, this maybe becomes lack of validity. The noise is really dominating the signal there. So this is kind of hard to suss out because definitionally we don't observe someone's true score. But there are some steps that we can take to check validity. So for example, we can at least see if the measure is reliable, which is what we'll do when we build scales. What this means is that we check how closely items in a scale relate to one another. If a scale is unreliable, it can't be valid. So one thing you can do is if you have a composite measure, or if you're worried about validity, you could construct a composite measure, and then you could see, do these items have much in common? And if they do, if they have a strong signal relative to the noise within them, then what that means is that you're capturing something here. You have some kind of reliability is the term we use, which means that there's some kind of coherent concept being measured. Then, if you can be pretty sure that the concept corresponds to your construct, you could say that you would have validity in that scenario. So there's kind of ways to check it. So that brings us to the end of the lecture. I know that's been a lot, so I want to give a quick summary here. Surveys are good tools for asking questions about objective characteristics of a large number of people, but any sample statistic is going to differ from population parameter for, among other things, random error. We try to minimize the mean squared error of the sampling process. We can decompose that mean squared error into two sources, the bias and the variance. Bias is basically the difference of the average of all the sample means from the true population average. In theory, in a lot of cases, those should be the same. So we should have an unbiased estimator. And then we've also got the variance, which is just the spread of the sample means around the mean of all the sample means. If we don't have any bias, then that's just the spread of all the observations around the true mean mu. But sometimes we do have a bias term, so we have to kind of concern ourselves with that. But in this scenario, for instance, then we could just limit it to basically the spread of the observations around the true sample mean, or the true population mean, pardon me. And that's basically just the noise that's inherent in the process of sampling. But it can be larger or smaller for different reasons that I mentioned before. And those bias and variance terms come from problems in representation and measurement. Thanks everyone for watching. Hope this was a comprehensive but accessible introduction to survey research.